Hello and welcome again. So today we'll be continuing the course graphs, theory, application, algorithm, and implementation. So we'll start with our first chapter, real chapter, which is about the basic concepts of graphs. But before that, let me just cover what we will do in this course. So we have started with a brief introduction about C++ for graphs. So we have seen the dynamic vectors, how we can search and sort vectors, and also we have seen some data structures like stack queues, DAX, and priority queues that we'll be using them while developing and implementing most of the algorithms in graphs. So today in basic concepts, we will see what does it mean a graph, and we'll see how we can model real-world applications using graphs, and then talk about types of subgraphs and graphs, and then check how we can do isomorphism between graphs, so to check whether they are equal in a sense, and then end with some graph operations. In the part distance, in the chapter distance and matrices, so we'll see how we can represent a graph using a matrices. So we have different type of matrices, adjacency matrix, incidence and distance matrix, and we'll end with the implementation of a graph. So how we can implement a graph, especially those type of matrices. As for the graph algorithm, so it will be mainly directed toward how to search a graph. So we'll cover the DFS and BFS algorithm. So we will implement them and we try to find the connected components, and we will end with some applications like tree code, especially proof of code and the binary addressing code. As for the graph coloring, so we'll see how we can color vertices and edges. So we'll talk about the independent sets. We'll do some algorithms, and also applications, and we'll end with an introduction to Ramsey theory. For the minimum spanning tree, so we'll talk about trees, obviously, how to calculate minimum spanning trees. So we will cover two algorithms, namely Kruskal's and Prim's algorithms. So we'll implement them, and also we'll see how we can detect the graph edge property via the DFS spanning tree. For the connectivity chapter, so we'll cover the concepts of connectivity, and we'll do some application, and we'll implement an algorithm on how to find the articulation points and bridges in graphs for bipartite and matching. We will characterize what does it mean a bipartite graph. We'll do examples on job assignments, and we'll implement on how to find the maximum cardinality bipartite matching via what we call an augmenting path algorithm. As for the Eulerian and Hamiltonian graph, so we'll discuss what does it mean Eulerian graphs, how we can check and if a graph is Eulerian, and then we'll talk about Hamiltonicity. The same, we'll do some applications, namely the Chinese postman problem and the traveling salesman problem. We will end with some algorithms and implementation, namely we will write an algorithm on how to check if a graph is Eulerian, and we'll try to find the Eulerian circuit and trails using two algorithms. The first is Fleury's algorithm, and the second is Hale-Holzer's algorithm. For planar graph, so we'll talk about planarity and how we color graphs if they are planar, and of course we will end with some applications. For the digraphs, so directed graphs, so the last three chapters are the most important ones. So in digraphs, so they are directed graphs. So we'll see about what does it mean, and we'll talk about tournaments, the critical path methods, and we'll implement many algorithms. The first is topological sort using Tarshon's algorithm and Kahn's algorithm, and then we'll see how we can find a strongly connected components also using two algorithms. The first is Tarshon and the second is Kosaraju's. The distance in networks, so we'll cover two parts. First, the single source shortest path in unweighted graph, and then in weighted graph using Dijkstra's algorithms, and for graphs with negative cycles using Bellman-Ford algorithms. And then we will cover the all pair shortest path. So we'll have two solutions. The first is based on Floyd-Warshall's, and the second on the transit closure of Warshall's algorithms. As for the last chapter, so it will be about a flow. So we'll cover about the minimum cuts, the minimal cuts, and we will cover two algorithms on how to find those, especially the Ford-Farquharson method and the Edmond-Karbs algorithm. So in the model page, you have also some supplementary resources. So there are 3 books that you can check, and there are references that you can use them whenever you want to check any additional concept. So in today's chapter, the basic concepts, so we will cover graphs, so what does it mean and how we can model them mathematically. We will see some types of graphs, what does it mean, subgraph, supergraph, and then talk about trees, which are a special kind of graphs, and they are very, very used in other courses like in data structures. We have also, we covered the isomorphic graph, so how can we check whether two graphs are isomorphic, and we'll end up with some graph operations. So just to know that our graph is not the usual graph that you have covered earlier in the first year or in school. So it's not a function that's plotted over an XY coordinate system. So this is not our graph. Our graph is like this. There are points and segments. So our points, we call them vertices, vertex, and the link that join two vertices is called edge. So this is why in our discussion today, the first part, so we'll discuss what does it mean a graph and how we can model it mathematically, and we will cover some real applications in order to motivate why we are taking this course, and it's a very important course. So as I have said, whenever we are talking about a graph, so a graph is a mathematical representation of a relationship. So we have a graph that consists of two sets. So a graph J consists of two sets. I have a first set which is a non-empty finite set, so it's finite but it's not empty, so it's the set of vertices V, so those are the circles, so it's called vertices. And I have a set of edges, so the edge, it connects two vertices. So vertices, so whenever I'm talking about the graph, so I have two sets, I will repeat. So a set of n vertices and a set of edges. So a quick question, let's list the vertex set and edge set of this graph. So the vertex set of this graph, so this is the vertices, so I can list those vertices. So they are A, B, C, D, E, and F. As for the set of edges, so the set of edges, they are the length, the links between any two vertices. So I have AB, BC, for example, I have AD, BF, DF, and that's it. So those are the vertices. So this is the set of vertex and this is the set of edges. So we have the order. So the order of the graph is the cardinality of the set of vertices. So the order, it means the number of vertices. So what's the number of vertices in this graph? So it's 1, 2, 3, 4, 5, 6. It's 1, 2, 3, 4, 5, 6. So the order of this graph is equal 6. The size is the number of edges. So it's the size of the set of edges. So I will count them 1, 2, 3, 4, 5. So the same if I count them on the graph, they are equal to 5. So the order is the number of vertices in the graph, so the number of circles, and the size is the number of edges. So a loop, it's an edge that connects the same vertices. So it's, for example, here AA is a loop. Also, so a multiple edge, it means that the edge AB, it will appear many times in the set of edges. So we know that a set there is no repetition, but in case there are some graphs where they allow multiple edges, so this is a kind of multiple edges. So in the set of, so let us write the set of vertices of this graph. So it's equal to AB, and the set of edges, it's equal to AA, AB. So I can repeat also AB 2 times. So as you can see, I have here a loop because I have an edge that connects the same vertex, and I have a repetition. I have multiple edges between A and B. So those graphs, we call them multigraphs. So we will not be covering multigraphs in our course. We will cover simple graphs. So a simple graph, it has no loops and it has no multiple edges. So in our course, we will just consider a simple graph. So we will stay in the same graph. So we say that a pair of vertices are adjacent if there's an edge that connects between them. So for example, here A and B are adjacent. Why? Because there's an edge that connects A and B. A and E, they are not adjacent because there is no edge that connects between them. A and C, they are non-adjacent because there is no edge between A and C. So whenever there's an edge between two vertices, they are called adjacent. Otherwise, they are called non-adjacent. So We have also the notion of degree. So whenever I have a vertex V, I can calculate the degree of a vertex. So the degree of a vertex is the number of vertices adjacent to V. So let's do that on this graph. So what's the number of vertices that are adjacent to A? So I can count 1, 2. So the degree of A is equal to 2. As for B, I can count 1, 2, 3 because there's 3 links, 3 edges that goes from B. So this is 3. For C, it's equal to 1. For F is equal to 2. For D is equal to 2. And for E is equal to 0 because it's connected to none of the other vertices. So we can say that, so we have calculated degree. As for the incidence is for edges. So we say that edge, for example, AB is incident to A and incident to B. So incidence is for the edges. So it incidence to both ends of the edge. So, and also, so if I have a vertex A and B, AB in this, or sorry, if I have an edge A and B in the set of edges, then we can say that A is neighbor of B and B is neighbor of A. So they are neighbors because there's an edge that links those two vertices. So those are the notions. So we will cover more definitions about graph because it's a very broad subject. So let's have a quick question here. So let's say that the vertices of this graph represent a group of students, and we suppose that two vertices are adjacent, so A and B, for example, if the corresponding people have worked on homework problems together. So before trying to see the question, so we know that A have worked with B, A also worked with D, D worked with F, B with F, C worked only with B, and E was a standalone student. He doesn't work with anyone. So we have two questions here. Who has worked on homework problems with the most number of colleagues? So if I want to look well, I will see that B, he worked with A, C, and F, and it's the most, it's the person who have worked with the most number of students. So as you can see, this is the vertex with the highest degree. The second question, who has never worked on homework problems, any of his colleagues? So obviously E, because it has the degree 0. So as you can see, for a real-world problem, I can model this real-world problem using a graph, and I can calculate the degrees in order to answer this question. Let's also consider the same graph, and here we suppose that the vertices of G represent the computers in the lab, and the edge indicates that the corresponding computers can communicate directly. So we have a direct connection, so as if we have a cable between both PCs. Assuming that the computers all have the same speed and memory capacity, which computer would be the most appropriate as a network server? So they are telling us which one do you pick as a server. So such a computer should be able to communicate directly with as many other computers as possible. So obviously the answer here also is B, because B is the best choice to be as a server, because B has the largest degree, so it can connect directly to many other vertices or PCs as in this question. So they are telling us which computer is completely isolated from the network server. So obviously is E is completely isolated because there is no link between E and the server B that we have picked. So an isolated vertex, so it's a vertex of degree 0. So for example, E is an isolated vertex because it has degree 0. Whenever we have a degree 1, we call it an end vertex or a leaf. So whenever we talk about trees, we will see that a vertex with degree 1 is a leaf. So we have also two important roles of the degree. So we have the small delta and the big delta. So the small delta, which it is the minimum degree in the graph, and the big delta is the maximum degree in the graph. So if I want to recheck here, so I have the minimum degree here is equal to 0, and the maximum degree is equal to 3. So we'll see later, it will have a very repercussion about other types of graphs. So we just know that a small delta, it means minimum degree, and the capital delta is the maximum degree. So whenever we have delta, the small delta is equal to big delta, so whenever I have, it means that all the degrees are the same, we call the graph irregular. So I'll give you an example. Let's take this graph, ABC. So the set of vertices, they are ABC, the set of edges AB, B, C, CA. if I want to calculate the degrees, I have here 2, 2, 2. So for this graph, small delta is equal to 2, which is equal to big delta. So this graph is called irregular. So let me give you another example for irregular graphs. Let's say I have 3 regular graphs, so I need to have so let's do this. So I have 4 vertices, I have many edges. I will calculate just the degrees. So I have here 3 edges that goes from this vertex. I have 3 here, I have 3 here, and I have 3 here. So this is a regular graph. And also, so we say that a graph is R regular if all vertices are of degree R. So for example, this graph is 3 regular. So whenever we tell you that draw, for example, 4 regular graphs, so we know that you need to have all the vertices, they have degree of 4. So this is also a very known, and we'll use them a lot later in this course. So regular, it means that all the vertices have the same degree. So I just want to talk about Euler, Leonhard Euler. So Euler is a Swiss mathematician. It was born in 1707 and died in 1783. He's one of the most prolific mathematics of all time. He has more than 800 papers and books. And the trick is that he was totally blind when he produced most of those papers. So his name is not Euler, it's Euler. And usually graph theorists refer to Euler as the father of graph theory. And you will see that many of the algorithms and many of the theorems, they have the name of Euler. So they are all Euler, but every time we have different theorem. So Euler, one of his theorems is that whenever we have a graph, the sum of the degrees, so I write this, so sum of the degrees in a graph is equal twice the number of edges. So this is easy to prove, because every edge it will contribute twice to the degrees. So I will count this edge, one here and one here. So this is why it's equal to double the number of edges. So we have some corollary. So from this we can deduce other stuff. But however, in our course we will not do the proofs. So because we are doing computer science, we are not interested in the proofs of these theorems and corollary. So we have in graph G also. I have the sum of the degrees. So it's obviously it's 2 times the number of edges. So it's an even non-negative integer. So it's even and it's a non-negative. And we can also deduce that every graph, so every graph G, it has an even number. It has an even number of vertices of odd degrees. So also we can deduce that for every graph has an even number of vertices of odd degrees. So directly from this we can deduce that if we have a question like this, is there a 3 regular graph on 9 vertices? So obviously no, because if I have a graph, so if it has, so whenever we have an even number of vertices, they should have odd degrees. So here we have a 3 regular graph. It means all the vertices, all the 9 vertices, they have degree 3. So so it's impossible to have that. So let us do it quickly. So I have 9 vertices. So we know that the number of the degrees, sum of the degrees is equal to times number of edges. So sum of the degrees is equal 9 multiple 3, because each edge is equal to 27. So obviously I cannot have, so 27 is the sum of the degree, it's not an even number. So obviously I cannot have this. So there's no need to continue to calculate the number of edges, because I cannot have this equality, because it should be even. So we cannot have a 3 regular graph on 9 vertices. So it's very easy to see that. So let's move. So in graph, we represent vertices, so the circle. So it could be people, computers, or cities, as we have seen. And an edge are the edge. It's a link that links those vertices, those people, those computers, and stuff. So we'll see different ways to represent these. So in mathematical models, so they are used to abstract and simplify real-world problems. So in order to more understand these types of connections. So this is why we will cover some examples. So first with application example on chemistry. So we have here hydrocarbon called butane. It's composed of hydrogen atom and carbon atoms. So they are telling us, give us the set of vertices and edges. So we need to represent this atom, this hydrocarbon, using graph. So it's very easy to see that I have vertices here and I have some edges because I have some links that links those type of hydrogen and carbon atoms. And also we have two types of vertices. One is carbon and one is hydrogen. So if I want to just draw this graph, so I will see that I have four major carbon atoms. So at the end I have three hydrogen. I have a link here between all these. Each one of these, it has two atoms of hydrogen, and this one it has three. So if I want to name those vertices, for example, I will call them C1, C2, C3, C4, and I will start by H1, H2, H3, 4, 5, 6, 7, 8, 9, 10. So what is the set of vertices? So it's equal to C1, C2, C3, C4, and I have from H1 till H10. As for the edges, I have a lot here. So I have, for example, C1, H1, C1, H2, there's no comma here, C1, H3. I will list all these, and I will end, for example, with C4, H10. So in total, so I have 14 vertices and I have 13 edges. So this is an example on how we can represent a real application in chemistry using graphs. I can do a lot of stuff later on when we cover the different aspects of graphs. Another application is the business warehouse retail store. So I have a graph here. So I have warehouses. So I have three warehouses and I have a retail store. So in this application, they are telling us that a warehouse can service a retail store. So we have a warehouse, so where there's a stock, and whenever a retail store needs some merchandise, they can get it from its warehouse. So they are telling us which warehouse service the most retail store. So I have here three warehouses. Which one it services the most retail store? So obviously I have here the degree 2, I have degree 3, I have degree 2. So this is the most. This is the warehouse that serves the most retail store because it gives merchandise to three retail stores. They are telling us if store R2 needed merchandise, so it needs merchandise, but W2 was out of stock, so you cannot supply W2. So which warehouse might be able to service R2? So from where R2 can get his merchandise, so obviously it can get it from W1. So we will talk here about what does it mean a bipartite graph. So as you can see, we have two sets of vertices, the W's and the R. As you can see, those three, they are not connected. So they are disjoint, there is no overlapping, and those one, they are not connected. So we have two sets, they are not connecting. So we call this type of graph as bipartite graph. So whenever we have a bipartite graph, we have a graph, it has two parts. So the set of vertices of this graph is disjoint. So we have two parts in the set of vertices, two disjoint sets that partition the set of vertices. So if I want to write this set, so obviously I have one set of vertices, but they are disjoint. There are no links. There's no links between those three and those five. So we'll see how we will use the bipartite graph, especially when we want to do matching between the vertices. A third example is the distance between two cities. So here we have a graph where it represents cities. So A, B, C, and D, E, they are cities. And the number here is the distance between the two cities. So for example, to go from A to B, I need 320. To go from A to D, I need 500. So this graph is called a weighted graph. Why? Because the edges, we attach to the edges some weight, some number. It could be positive, it could be negative. We will see that later whenever we work with distances and flows and networks. So the question here is to find the shortest path. So also we have a new notion here about the shortest path to get from D to C. So if I want to go from D to C, this is D and this is C, I have two choices, either to go to take the road DABC or to take DEBC. So I have two choices and I need to pick the shortest one. So shortest, it means the shortest in terms of distance. So if I want to calculate the first one, so it's equal to 500 plus 320 plus 140, which is equal to 960. And the other option is to take a DE plus EB plus BC, which is equal to 940. So obviously I need to pick this one because the shortest one, and this is one of the most known application in graph, and this is why we use them to calculate the shortest path between any two vertices. And we will have a dedicated chapter for the shortest passes, for the minimum spanning tree, and for all this subject. So we'll cover that in details later on. Another application also is the ice cream truck routing. So we have an ice cream truck. So we have routes here, the edges are route, and the vertices are the intersection between the vertices. So the question here, if a driver begins at vertex 5, so our driver will start from here, can the driver travel along each street exactly once and return to the vertex 5? So he needs to travel all the edges, but just once. He cannot travel the edge more than once. So is it possible to find a route for this guy in order to loop over all this graph and return to 5? So it may take you some time to find the solution. However, we can try. However, there are other options. You will learn it during the course. So I can go from 2, 3, 1, 2. So I'm just trying to do a solution here. Maybe it will not work. So I have reached here. So I can go to 7, 10, stuff like that. Yes. And I have reached to do that. So I have traveled all the edges, and each edge I have traveled it just once, and I have reached to do that. So there's also many other solutions. So I can do it in the reverse order, or you can find also some other solutions. So we'll see about that. So if they are telling us here now, if this edges was not present, so we'll tell you that it will be impossible to find this, so we need to retravel some edges one more time. So whenever I can travel the edge one time and return to the starting point, we call this graph Eulerian. So Eulerian graphs is where I can travel each edge once. So this is a very important problem, and we'll see how we will deal with Eulerian graph. Another application is the traveling salesman problem. So I have here cities, so the vertices are cities, and we have a man that wants to travel all the cities and it will return to his home. So we have edge his home. So they are telling us, how can you accomplish this assignment if you are to visit each city only once? So he can visit the cities only once. So again, I need to try to loop over the city. So there are multiple solutions. I can go, for example, H to B, B to A to C, E, D, and H. So I have traveled each vertex 1. So there are many more solutions. So here in Hamiltonian, so we call it Hamiltonian graph. In Hamiltonicity, we just need to check whether we can travel each vertex once, and we'll see that whenever we are dealing with Hamiltonian graphs, this is not an easy problem. So it's very difficult to write algorithms to check this. So usually we need to relax the problem and do some to place some, for example, more requirements, restrictions, in order to be able to find a solution. Another application also is the scheduling exams. So I have here vertices. So vertices here means that whenever we have a course, so A, B, C, D's are course, and we link. So the edge here, the link between any two vertices, it means that there's a student that failed both courses and he needs to do them. So obviously I cannot schedule both exam A and B at the same time, because one student he has the same he has two exams to pass. So obviously I cannot schedule both exams. So in scheduling like this, one must ensure that no student has a conflict, and the vertices represent the courses, and we join two vertices if the courses have at least one student in common. So how we can solve that? We solve that using graph coloring. So this is a new concept also. So they are telling us scheduling exam is equivalent to assigning each vertex a color while assuring that courses connected by an edge have different colors. Can you do that? So can you color those vertices in the sense that there's no color at the same time between any two connected vertices? So obviously we can do that. We can use different types of algorithms. We have the maximum coloring, the minimum coloring. So the maximum coloring in the sense that I can color each vertex a color. So I will schedule, for example, here 6 sessions. So obviously this is not the optimal solution because I can join multiple courses at the same time. This is what we do at our faculty. So for example, I can color this red. So whenever I'm coloring this red, obviously I cannot color these two by red. I can color this blue. So now obviously see, I cannot color it red, but I can color it blue if I want to minimize the number of colors. As for D, it's connected to a vertex that is colored blue. I can color it red. So the same for E. E is connected to a blue and something which is unknown. I can color it red for now. And then I have here F. It's connected to a red, and blue. So obviously I cannot color it as red. I cannot color it as blue. I need to, for example, use another color, a green. So I have 3 types of colors. So I can schedule the exam only in 3 sessions. So I will place, for example, the red first, blue, and green. So the exams for the first session are A, E, D. So those who have the exam A, E, D, they will do it at first. And then we have the blue one, we have B, C, and then F at the end. So this is how we do scheduling or any type of scheduling using graph coloring. So we'll have a chapter dedicated to graph coloring where we color vertices, we color also edges. So we'll see the applications for those in the coloring graph chapter. Also an application is the assignment model. So here we consider a graph. So the vertices represents people, and an edge connects two people who are friends. So this is a friendship graph. So let's suppose that these people are planning to go on a long bus ride, and the organizer need to seat person in pairs. So the chairs contains 2 places, and he needs to place them in pair. So the question here, how you will seat them? So you will see that, okay, the number of vertices is even, so it's possible to do that. We will see that wherever the number of elements is not even, is odd. So obviously there is no a good assignment, maximum assignment. So let's try to do this here. So let's suppose I will sit Haneen with Ali, I will sit Danny with Eli, and Karen with Fadi. So now I cannot sit George and Bilal because there is no edge between them. So this is an assignment, but this is not an optimal assignment. This is not the maximum assignment because I could have distributed the students differently, and I can reach to sit Bilal with, for example, Fadi. So if I've chosen, for example, a different matching, so for example, if I sit George with Karen, Haneen with Ali, Bilal with Fadi, and Eli with Dani, it would have been more optimal because I have set all these students with their friends. So this is what we call a graph matching. So we try to match the vertices in a maximum possible way. So we will see that sometimes it's possible, sometimes it's difficult, and we will see how we will do that using our course, because we will have a dedicated chapter to bipartite graph and matching. So we have covered till now the most important applications in graphs. So we'll see why we are using them and how we'll cover them in our courses. And you have seen that all these problems are real-world problems that you can model and solve and implement using programming techniques. So we'll move to our next part, which is about subgraphs and types of graphs. So the outline of this part, so we'll talk about walks, Yes, there's a lot of definition about that. We'll see that it's very difficult to understand at the first, but you need to take notes about that because they are very tricky. Then we'll talk about types of subgraphs and then the important types of graphs. So we will first talk about what does it mean a UV talk. So whenever we have two vertices U and V, so UV walk is an alternating sequence of vertices and edges beginning from U and ending with V. So in practice, we list the edges. So UV walk, it means just a walk, as if you are walking in the graph. You are going from U and reaching V, and you are listing just the edges. So we'll do an exercise just in a while. So UV walk, we are just walking, so there's no restriction. You can walk, you can repeat the number of edges, you can repeat the vertices. This is not important. You are just walking. There's no purpose. You are just walking. Though the length is the number of edges of this UV walk. So the length is the number of edges. So remark, I will always repeat it. So edge can be repeated. So there's no restriction on the repetition on the edges. So a trail, so if no edge is repeated, so as if you are doing hiking, so if no edge is repeated, so obviously in hiking you don't repeat segments of road, no edge can be repeated. So in UV walk, you are walking, there is no purpose, so you can repeat, you can loop on yourself, so this is okay. So the number of edges in a UV walk is called length. The trail is whenever we have no repetition in vertices. So here vertices. So whenever we don't have vertices, we don't have repetition of edges. So obviously, and we say that a circuit is a closed trail. So whenever we start and we end at the same vertex, it's a circuit. So circuit is a closed trail. So we'll do an examples about these because they are very difficult to grasp at the beginning, because this is not just those definitions. We have a lot more to come. So we have also a pass. So pass, it means, so it's a walk, but no vertex is repeated. So it's a path, so no vertex is repeated. So walk, it means there's no purpose, it's just a walk. I can repeat everything. I have a trail, so no vertices can be repeated. I have a path, no vertex is repeated. What else? So we have a UV path. So whenever I have a path that joins U and V, so no vertex is repeated. So it's a path. It's a UV path. So we see that every UV walk, it contains a UV path. So since walk, it can repeat vertices and edges, obviously. So a UV path, it's in the walk. So every UV walk, it contains a UV path. So a path also is a trail, because an edge cannot repeat it if two vertices of the edges are repeated. So it's very obvious, because a path, it has no repeated vertices, so there's no repetition of edges. And a closed path, so a closed path is a cycle. So this is a closed path. It's very tricky between those definitions. So just to know that in our cases, we will not be too much concerned about the differences between all these, because we mostly will be concerned with calculation of shortest paths. So we call paths, so there's no repetition in the vertices. So this is what we intend to do. So we will be interested more in paths, not in trails, not in walks, and not in other parts. So we just need to remember path. So path, because we will talk about shortest path, so there's no repetition of vertices. So I cannot loop many times on the graph. So if I have A, B, C, and then CA, so this is a normal graph. So in our talk, we will not do, for example, ABC, ABC, ABC. You know, even if it's possible, we will not repeat this path. So usually we have a path, so from A to C, from A to B, from C to A, but we will not loop infinitely into this. So we talk mostly about passes and a cycle. So also we'll do an example later on about these notions. So we have a theorem here. So if every vertex of a graph has degree at least 2, then the graph contains a cycle. So we have that if graph contains, so if at least, so if delta, for example, of j is less or equal to 2 implies that j has a cycle. So also we know that if delta is less or equal to 2, so it's not equal, it's greater or equal to 2, so it has a cycle. So we know that it has a cycle of length, so we know also the length of delta plus 1, and we know also it contains a path, so j has a cycle of length delta small delta plus 1, so this is minimum degree plus 1, and it has a path of length delta of j. So whenever a graph has the minimum degree is greater or equal to 2, I can have these. So I have a cycle of length delta plus 1 and a path of length 2, at least 2. So it's equal to delta. So we have an example here quickly. So first they are telling us find the minimum degree of graph. So the small delta is the minimum degree. So I have here 2, 2, and 2. So delta is equal to 2. So also this is a 2 regular graph because all degrees are equal to 2. I need to find a path of length delta. So obviously I have a path of length delta because this is the theorem. So all the paths are equal to delta. I have A, B, B, C. So this is a path. I'm going to A to C. I can also have a path of length 2 from A to B. It's equal ACB and so on. So I can find a path of length 2. I can find a path of length less than 2. So for example, I find AB. This is a length 1, but I can find a path of length 2. Find a cycle of length 3. So for example, ABC. ABC, this is a cycle of length 3 because I have traveled 3 edges and it's a cycle. So I start with A and I will end with A. So this is the proof of, not proof, just an example on if the delta is less or equal to 2, is greater or equal to 2, sorry, it means that I can find a path of length delta and I can find a cycle of length 3. So let's now talk about the walk trails and paths and see how we can do this. So first, I have this graph, so it has many vertices and edges, so we can list the set of vertices and list the set of edges. However, they are asking us to find a walk that is not a trail. So a walk that is not a trail, it means it can repeat edges, because a trail, it means I cannot repeat edges. So it means you should repeat edges. So find a walk that is not a trail, it means repeat edges. Please repeat edges. So I can repeat, there are multiple options here. I can, for example, go from G to E, E to G. So this is a walk that is not a trail. So I can give you a more reasonable example. So for example, G, E, I can go to B, I can then go to C. I can also go to B, B to E, and E to D. So this is an example of a walk that is not a trail because I have repeated edges. And we know that in trail, I don't repeat edges. Then they are asking us find a trail that is not a path. So it means you can repeat vertices, but it's not allowed for passes. So you need to repeat vertices. So I need to find a trail. So we know in trail that there's no repetition of edges, and in passes there's no repetition in edges, and in trail I cannot repeat edges, but I can repeat vertices. So what does it mean that? So for example, if I'm in E, I can go EB and then I can go EC, for example. So I can revisit the same vertices multiple ones, but I cannot revisit the same edges multiple times. So again, here I can have many options. So for example, I go from G, I go E, I go then D, and then I go C, I go B, I go E, I go C. So as you can see, I have revisited E 2 times. So this is a trail. It's not a path. So a trail because I didn't visit an edge more than once, but I have visited a vertex more than once. So this is the difference. So then in part 3, I need to find 5 BD passes. So path, there's no repetition of vertices and there's no repetition of edges. So let's see how we can find a BD path. 5 different BD paths. So I can go BCD. This is 1. So I will write it here. I can go BED. I can go also BCED, so this is also a valid option. So also the opposite, BECD, and there's also another one, so I can go BAFCED, BAFCD. So as you can see, there's multiple passes. So if I want to talk about the shortest path between B and D, so obviously it's equal to 2 because I need to just travel 2 edges. So those ones are shortest passes. Those are just passes, but they are not shortest. So we'll talk about it while. What does it mean shortest path and what does it mean geodesic path? So they are telling us determine the length of each path. Oh, we have already done that. So we have 2, 3, 3, and 4. So, and obviously we will pick 2 if you want to pick the shortest path. So find a circuit that is not a cycle. So it means that I need to repeat vertices, but I will not repeat edges. So I can repeat vertices, but I will not repeat edges. So I want to go from C to C, and I can repeat vertices. So also there are multiple options. So I can go C, B, A, F, C. I can go also E, D, C. So I have made 2 loops. So I have visited C multiple times, even if I have a circuit. So I have repeated vertices, but I didn't repeat the edges. So they are telling us find all distinct cycles that are present. So how can I find a cycle? So we can try to find cycles by length, for example. So I have this here, so I, J, H, I have E, D, C, E, I have those ones. So this is, for example, a cycle. So I have here 3 cycles of length 3. We have also of length 4. So we have A, B, C, F, and we have E, D, C, B. So those are a cycle 4. We have also 1 cycle of length 5 and length 6. So you need to practice this. So the length of length 5 is equal to A, B, E, C, F, A. And also we have a length 6, so it's also visible here. It's equal to A, B, E, D, C, F. So it's a length, the cycle of length 6. So in cycles, there's no repetition of vertices and no repetition of edges. So I repeat, you just need to know about passes and cycles. So a pass, no repetition of edges, no repetition of vertices, and in cycle, so it's a pass, but it's closed. So in the practice, you will not have questions about these. Don't worry, you just need to grasp the idea of passes and cycles. So a graph is connected. We say that the graph is connected if every vertices, they are connected in somehow. So there's a path, a UV path that connects those 2 vertices. So for example, I have here E and J, so they are connected. Even it's not directly connected, but there's a path, there's a UV path that connects E to J. Otherwise, we say that it's disconnected. So for example, if I have a vertex, a P somewhere in the graph here, so obviously the graph is disconnected because I cannot find, for example, a BP path. So there's no BP path between those 2, so we call them disconnected. So a shortest path. So for example, if I want to find a path between what we say A and D, so I can go AFCD or I can go ABECD. So obviously this one, it has the UV path between AD, so its length is equal to 3, and this one is equal to 4. So this one we call it a shortest path, or we call it a geodesic path because it's the shortest one in terms of length. So as for the subgraph, so we know that a graph, it has 2 sets, the set of vertices and set of edges. So a subgraph of G, so obviously it's a subset. So for all these, so if a graph has a vertex set and an edge set, and let's say that H is a subgraph of G, so obviously it has a vertex set and an edge set. So the vertex set is a subset of the vertex of G. It could be equal, it could be included, and the set of edges is a subset of the set of edge of the graph G. So obviously we need to preserve the same edges. So obviously in the subgraph, obviously I will not encounter any new edges if it's not present in the original graph. So usually how we obtain the subgraph edge, we delete some edges or we delete some vertices from the original graph. So, and whenever we have a graph edge, so it's the graph J, it's super graph, so it's the reverse definition of a subgraph. So J is a super graph for edge. So let's see examples here. So I have here a graph G, and here I have a graph H. So as you can see, I have in graph H, it's a subgraph of G because I have removed F. So obviously I will remove its edges, and also I have removed some of these edges. So I have removed the edge AE, the edge AB. So this is H is a subgraph of the graph G. So they are telling us in this exercise to draw all subgraphs of the graph G that uses the set vertex A, B, E, F. So they are telling us, please, the set of vertices of H, it contains just A, B, E, and F. So remove D and C. So don't take into account the other vertices. So obviously the other edges. So how many is the number of the subgraph, or draw all the subgraphs? So I need to sometimes keep all the edges, sometimes remove all the edges, and so on. So I have drawn all the subgraphs. They are equal to 16. So I have kept the vertices, and obviously from the remaining edges I have included one. I have took all the combinations. So we have in total 16 subgraphs. So we move to a more important notions whenever we are talking about a subgraph is the subgraph induced. So we call that whenever I have the set of vertices of a graph J, and let's suppose I have picked a set S of these vertices. So we say that the graph is induced is whenever the graph that is consisting of the set of edge S contains all the edges from the graph G. So I will repeat. What does it mean induced by S? It means I have chosen a set of vertices like we have done earlier. Induced, it means that from this set I have kept all the edges. I didn't remove any edge from the vertices that I have kept. So this is what it means induced. So we'll see an example in a while. So a labeled graph is a graph whose vertices have labeled. So as we have seen, so it has names attached to them. So if it's unlabeled, it means it has no labels attached to that. So what does it mean spanning a graph? So we have seen what does it mean induced. So induced, I will repeat. It means that I have a graph S, I have graph G, I have picked a set of vertices from this graph. It could be all, it could be part of it. And so the subgraph induced by us, it means that I have kept all the vertices that I have chosen by us and all the edges from the graph. So I have kept all the graph. So spanning, it means it's induced, but spanning, it means the set of vertices of J is equal, of G is equal to set of vertices of H. It means that I have kept all the set of vertices, but with a minimum number of edges. So I will repeat. So a subgraph H of graph G is called the spanning subgraph if we have the set of vertices is equal to, they are equal. So we say that H spans J. So we'll see later on, we have a course related to minimum spanning a tree. So let's see an example here. So I have here a graph. This is induced subgraph. So as you have seen, so I have picked a set S. It contains just 1, 2, 3. This is the set of vertices. So I didn't choose 4, but I have kept all the edges from the original graph. This is not induced but spanning. So why it's not induced? Because I have kept all the vertices, so it's spanning. So I have removed one of these edges. So I could have removed this one too, but this is not a minimum spanning tree. So here I have talked about minimum, but it's not important to have the minimum number of edges. The important is to have the equality, is to have the number of vertices which are the same. So Let's continue. So we have here a revisited graph slide. So as you have seen here, we say that this graph is connected because all the vertices are, there's a UV path between each of them. So this graph is not connected because, for example, there's no UV path between A and B. So this is what does it mean, connected and disconnected. So in a disconnected graph, the various pieces of the graph are called components. So for example, here I have 1, 2, 3 connected components because I have 3 different parts. Here I have 1 connected component. So a component is a maximal connected subgraph. So it's maximal connected subgraph, and we say that one vertex is a maximal connected subgraph. So as a quick question, so how many connected components there is in each of the subgraphs? So we see here that we have 1 connected components because they are all connected. Here we have 2 connected components. So this is the first maximal connected components, and this is the second. Here we have 3, and here we have 4 connected components. So let's move to important types of graphs. So we have complete graphs and trivial graphs and clicks. So we say that the complete graph, it's denoted by k of n. So you need to learn these. So or we call it a click. So it's the graph with all pair of vertices are adjacent. So it means there's an edge between every all vertex. So we know that the set of vertices of kn is equal to n. So whenever we tells you draw, for example, k2, we know that there's 2 edges. Whenever we tell you draw k5, you know that there's 5 vertices. And the number of edges of kn, it's equal to n multiple n minus 1 over 2. However, in the theory, they write less or equal to n minus 1 over 2. So this is an example of k5. So let me draw you, for example, k4. So k4, it means I have 4 vertices. 4 vertices, and it's connected, so it's complete graph. So there's all connections, and there's all the edges. They are all adjacent. So they are all adjacent. This is the K4. So as you can see, K4 is 3 regular. So let me give you another example. Let's say about I will not draw K6, it's too much. So let's draw K6. So K6 means I have 6 vertices, and they are all adjacent. So this is K6, and if you can see, K6 is 5 regular because each vertex, is of degree 5. So graph Kn is the unique connected n minus 1 regular graph on n vertices. So K1. So K1, what does it mean K1? It means 1 vertex. So this is K1. So K1, we call it a trivial graph, and it's complete. So even if it's 0 regular, so it's complete. We have also a cycle. So cycle, as does it mean there's a cycle. So we call them Cn. So this is true for n is greater or equal to 3, because if n is equal to 2, a cycle would look like this. So it's like as if there's another edge, and we are not considering multigraphs. So our cycles begins from n greater or equal to 3. So if I want to draw C3, for example, C3 is like this. And if I want to draw K3, it's also the same. So as you can see, C3 and K3, they have the same graph. So K3 is the complete graph, which is 2 regular. So C3 also is 2 regular. So this is C6. So as you can see, C6 also is 2 regular. So all cycles are 2 regular over n vertices. So they are always connected to 2 vertices. Each vertex is connected. It has 2 neighbors. We have also a path. So also we have a type of graph which called a path. So path, it means it connects n vertices. So we call it usually P of n. So this is P4. So P4 because we have 4 vertices. So the degrees of P4, they are 1, 2, 2, 1. Let's see, for example, for K1. So K1 is just a vertex, and P1 also is just a vertex. So P1 is equal to P1. Also, if I will draw K2, so K2, this is K2, and P2 is the same. So also P2 is equal to P2. And as you can see, I will erase all these. If I want to draw a cycle C4, this is C4, you can see that P4 is a spanning of C4. So it's a spanning subgraph of C4. We just need to delete a single edge. So it's spanning subgraph, because I have kept all the vertices and I have removed some of edges. So here it's the minimum spanning, but let's call it spanning for now. Another type of graph is the complete bipartite graph. So we have seen what does it mean, complete graph. So there are edges between all the vertices, they are all neighbors. And bipartite, it means I have two sets. So usually we represent it as K and M, where N, because bipartite, it means the set of vertices, I can split them into two disjoint sets. So here, for example, in the example, I have K2, 3. So the first, I have first disjoint sets with 2 vertex, and the second one with 3 vertex. So when we have N is equal to M, so for example, I have K and N, it means that, for example, I have 2, 2, 2, 2, they are all connected. We say that the graph is irregular, you know, because I have 2, 2, 2, 2, and the number of vertices, they are equal to 2, 2, so it's irregular. In this case, it's not irregular. So this is the complete bipartite graph. So we have a special case which is called a star. This is a star wherever we have K1n. So in K1n we have the center vertex which is 1, because it's also bipartite and complete bipartite, and n is the number of leaves. So we have already covered or end vertices. The vertex with degree 1, they are called end vertex or leaf. So K1n is called a star because it looks like a star. So usually the degree here is equal to n because it connects, it's connected to all other vertices. So this is the part concerning the graph types and subtypes. So you need to learn these, because later on we will not draw graphs. So we'll see, okay, what about K1, what about K2, give us the number of edges to note of this and this, especially in the practice. So you need to learn or to memorize what does it mean K, what does it mean P, C, and stuff, and those types of graphs. We move into trees. So trees are a special type of graphs. So I have here some notes that they are very important. And a graph, it has the property that no subgraph is a cycle. So a graph, whenever it has a tree is called acyclic. It means there's no cycle in the trees. So a connected acyclic graph is called a tree. So this is very important. So there's no cycles and it's always connected. So there's no connected components and it's acyclic. This is very important. Whenever there's no cycles, it means that there is always passes. So I cannot repeat stuff since there's no cycles at all. So there's always one pass, and it's always the shortest pass. So that telling us that trees are the basis of important data structures. Oh yes, we will see that in data structure later in the second semester. And the tree is a special type of bipartite graph. So we'll see why is that very important. So till now we have seen two types of trees. We have seen the stars. So stars are trees because there's no cycles, and all the passes are geodesic, are shortest passes, and also passes. So P4, P5, those stuff, there are no cycles. So if I want to go from here to there, there's always one way. There's no many ways to do that. So the passes P, so maybe defined as a tree on n vertices, such that the maximum cardinality, so the maximum degree of this pass is less or equal to 2. So we know that all these of degree 2 and the extremities are of degree 1. So also the star K1n is a tree, so it's order n plus 1, so the number of vertices is equal to n plus 1, and the degree of the central vertex is equal to n. And we have also talked about leaves. Those are the end vertices of tree. So it's always, whenever we have the degree equal to 1, we call those vertex leaves. So they are giving us here an example of a tree with 14 vertices and 13 edges. So the vertex are A, B, C, D, and all stuff, and the edges are the one that connects the vertices. So as you can see, there's no cycle. There's no multiple UV passes between any two pair of vertices. So we have some 4 properties about trees that are very important. So we say that every non-trivial tree has at least 2 end vertices, except K1, obviously. So any tree, it has at least 2 end vertices. It has at least 2 vertex of degree 1. So at least 2 end vertices. As for property 2, they are telling us that if you delete one of these edges, the graph will be disconnected, the tree will be disconnected. So every edge, we call it is a bridge. So we'll cover that later whenever we cover connectivity chapter. So it's a bridge, or we call it cut edge. So if we remove one of these edges, the tree will be disconnected. So whenever we are constructing, for example, a road, and if the road is blocked, all this part will be blocked. So this is the idea of the bridges, and we'll see later what does it mean, a cut vertex and cut edges. Also, as I have said, all the UV passes are shortest path and geodesic passes, because there is no other route, there's no cycles, so there's no other ways to do that. So all UV passes are geodesic, or you can say they are shortest passes. As for the fourth property, so a tree with n vertices and q edges, so n vertex and q edge, we know that q is equal to n minus 1. This is very obvious. So a tree is minimally connected since there's no loops. So if I have this tree, so I have 1, 2, 3, 4. Obviously, I have 3 edges. So always the edges is equal to number of vertices minus 1. So even if I can calculate the number of leaves, so we have a formula. So let me write it for you and then explain it. So I have n1. This is the number of leaves of degree 1 is equal to 2 plus n3 plus 2 and 4 plus 3 and 5 plus. It's equal to 2 plus sum from I equal to 3 to infinity. So we don't know the number of degrees in a tree. It could be 5, 6, 7. So infinity here means the maximum degree. I minus 2 multiple ni. So given a non-trivial tree, we denote ni as the number of vertices of degree e. So it's the number of vertices of degree e, and here we are calculating the number of degree 1, which is the number of leaves in a tree. So it's very interesting to know that the number of leaves, it's based on the number of the other degrees in the tree. So this is a formula that you can use, but we will not prove it in this course. We will move to a more interesting and difficult part, which is the isomorphic graphs. So in isomorphic, so we know that every person can draw a graph differently. So for example, those graphs are the same. However, one chose to draw the first graph like this, and the second one the graph like this, because there's no rules on how to draw graphs. So you have vertices, you have edges, and you can do that. So in the practice, you have a lot of exercises to draw graphs, and obviously everyone can do it differently than the other. But at the end, we need to compare and we need to check whether two graphs are equal or are isomorphic. So we are seeing here that here we have used the same vertex label. However, here I have different vertex label. However, you can see obviously that those graphs, their structure is the same, so it's isomorphic. So we will see how we will do that. So we have the notion of isomorphic and non-isomorphic. So we say that two graphs G and H are isomorphic. So we represent it like this. So if we can label these graphs in a way that the corresponding edges or vertices are adjacent. So if I can rename those vertex like those labels, and if I can preserve the adjacency, I can say that those are isomorphic. So usually this is more banal way to say that. However, more technically and more mathematically, I need to find a bijection between the set of vertices of the first graph and the set of vertices of the second graph, such that any pair of vertices that are adjacent in J, if and only if the function, this bijection, will preserve the adjacency in the second graph. So we call that function an isomorphism between these two. So usually mathematically this is what we do. So we need to find a function f that connects, that pairs. So for example, I would say a would be equivalent to 2, b would be equal to 3, c equal to 1, d equal to 5, and d equal to 4. So if I do this renaming, I will preserve the same adjacency here, and so this graph is isomorphic to the other one. So usually we will not do that because I will not be calculating isomorphism. So how more practically we can do that. So also before doing this exercise, obviously if the number of vertices is different, so if the size and the order of the graph is different, or if the number of vertices and the number of edges is different, so obviously there is no isomorphism, so there is no need to study that. So before doing the isomorphism, we just need to check if we have the same number of vertices and the same number of edges, and then we'll see if it's isomorphic or not. Just a reminder that usually isomorphism and non-isomorphism for large graph is usually very difficult to determine. And we will see later, we usually prove that two graphs are non-isomorphic, and we don't prove that two graphs are isomorphic. So it's more easier to find something that doesn't work, but it's very difficult to prove that two graphs are isomorphic. So we have here a small example. They are telling us to check if the two following graphs are isomorphic. So first, let's see the number of edges. So I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so it's equal. I have 3, 4, 5 edges, 1, 2, 3, 4, 5. So for now, it's okay. Let's see if I can find a function that can map all these. So first, I would like to do the degrees because it will help me to do this. So I have here 2, 2, 3, 2, 1. So I have one vertex of degree 1 and 1 of degree 2 and 3 of degree 3. So as a first side, I would link a to 4. So I would say f of a is equal to 4. And then I don't have any other choice. Obviously, if it will be isomorphic, I will link f of e equal to 3. Then I will look. So if I have 1 is connected to 2, I have 1 connected to 2. So I will link d to 2. I don't have other choice. Now, I still have two other vertices of degree 2. So C and B. So either here 5, I will link it to C, or I will link it to B, or I will link 2 to C, or link 2 to B. So let's pick one and see if it will work. So let's say C is linked to 5. If C is linked to 5, I will see if it preserves the adjacency. So I have 3A is linked to C. 3 is equal to 4, so yes, for now it's correct. And I need to check if C is linked to B. So B, it means the new one. So if I pick 1 here, it will work. So yes, f of C equal to 5 and f of A is equal to 1. So if I do also the opposite way, it will work also, I think. So as you can see, yes, I have found a bijection that preserves the adjacency between the vertices. So the number of vertex is preserved, number of edges, and the adjacency is preserved. So the two graphs are isomorphic. So since we need to preserve adjacency, so all adjacencies along a given geodesic passes are also preserved. So the minimum distance also should be preserved. So if I just want to redraw this, so it will be easy to see that I can draw 3 here, 2, and then 4, and I will pick 1 or 5 and say anywhere here. So it's easy here to see that. So, however, you need to pay attention about the, for example, later on we'll cover stuff that sometimes the geodesic pass is not minimal, so there's no geodesic passes are not preserved. So, we have covered the degree. So we have what we call a degree sequence. So we will see how a graph is, if it's graphical or not. So if we give you the degree sequence, is it possible to draw this graph? So let's just review this. So I have here the degree equal to 1, 2, 2, 1. So the degree sequence, we usually write them in decreasing order. So for example, for this graph is equal to 2, 1, 1. This is the degree sequence of P4. If I would tell you P5, so P5 is like this. So it will be equal to 2, 2, 2, 1, 1. If I want to draw C5, so this is C5, C5, so there's 5 vertices. So C5, all the degrees are equal to 2. So for C5, I have 2, 2, 2, 2, 2, 2, 5 times. So this is the degree sequence of a graph. So the question here, if I gave you the degree sequence, can you say that the graph could be drawn? Is it possible if I gave you the sequence could be drawn? So for example, if I gave you 2, 2, 2, is this a graphical sequence? Can I draw this? So if I want to say, okay, I have 3 vertex because I have 3 numbers and each one is equal to 2. So yes, it's equal to P3 is equal, sorry, to K3. So this is normal, or C3. So this is a valid graphical sequence. Let me give you another non-graphical sequence. Non-graphical, so let's say I have 3, 1. So obviously I need to have 2 vertex. However, it will be impossible to have 3 vertex, 3 edges here, because if I have 3 vertex, 3 edges, it means I need at least 3 vertex. So I need at least to link it to 3. However, there is 1. So this is obviously not a graphical sequence. I cannot draw this graph using this graphical sequence. So we'll see how we will do that. So obviously there's an algorithm to check whether a graph is or degree sequence is graphical. So given a sequence, how we can check if it's graphical or not. So graphical, it means I can draw the graph using the graphical sequence. So this is why we have an algorithm. So at first we delete the first number, delete first number. Let's call it K. What we will do next, we will subtract 1 from the first K number from the sequence. So we'll see now. So I will remove the first one. So I have the sequence. I will remove the first one. Let's say is equal to 3. I will count 3 numbers here. I will do -1 from each of these 3. Then, so I will do sorting. I will sort these values because I may have here a bigger number than those I have subtracted. After sorting, I will repeat until I have found a new sequence. So repeat until I have reached a stopping condition. So what does it mean, a stopping condition? We have here two ways. So either the sequence is all 0, or I know that a sequence is graphical. So for example, if I end up with something like this, 2, 2, 2, 2, 2, 1, 1, I know it's somewhere P, and I know that. So for example, 2, 2, 1, 1 is P4, 2, 2, 2, 1, 1 is P5. So I know that whenever I know that the sequence is graphical, I can stop because, okay, I have reduced the problem to a sequence that is graphical. So let's see more how we will run this algorithm. So I have this sequence and I need to know if it's graphical, if it's yes or no. So I will start like this, and then I have the first number, I will delete it, and I will subtract -1 from the first 3 numbers. Why 3? Because it's equal to 3. So I will do 2 minus 1, 2 minus 1, and 1 minus 1. I will end with this sequence. So this sequence is not a degree sequence because it's not in order. I will sort it. So in the practice, because you need to write this algorithm, you need to skip this part. So you need to subtract and directly sort. So this is, it's written in the practice exercise. Directly put the sorted result. So do the minus and sort it. Then we need also to repeat the stuff because we didn't reach the stopping condition. So I will remove the first one. I will deduct -1 just from the first number because it's equal to 1. I will sort and will continue. So then I will remove 1. And then it will be 0. So now everything is correct. So this is good. However, I could have stopped earlier. Why? Because this one, it's a graphical. So why it's graphical? So it's a, if I can look well here, so I have 1, 2, 3, 4. That means I have a graph with 4 degrees, it's equal to this one. It has one vertex, one edge. So this is 1, degree 1. This is degree 1. I have also 1 with degree 1 and 0. So before we do that, so there's also 1 here because I need to stop here. So this one, it means I have 5 vertices. 1, 2, 3, 4, 5. So let me do it correctly. I have one edge, so obviously it's connected to this. So I have 1, 1. I have also 1, 1. 1, 1, and this one is 0. So this graph is graphical because I can't draw this graph. So I could have stopped here and add the algorithm, and I say yes, this sequence is graphical. However, we have continued and till the end. So in the practice, you should continue till the end till you reach a 0. Let's do another example. So I have this sequence, and I need to check whether it's graphical. So as you can see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 vertices. So obviously I will give you a trick here. So whenever we have 10 vertices, the first one, obviously it shouldn't be 10, because if it's linked to 10 other vertices, it couldn't be graphical. So you have some types of these questions in the practice to just look at the sequence here and to know whether it's graphical, yes or no, before even trying to do the algorithm. So we know here that, okay, it's possible to be graphical. So let's start. I have 5, I will delete it, and I will do -1 from the first 5 numbers, for example, till here, and then I will sort. After sorting, also I will repeat, so I'll remove 3, and I will do that, and I will end up with this sequence. So obviously you can continue to 0, but you have known that is equal to one of the p's, because the extremity is equal to 1, and all the others, they have degree 2, so it's equal to 1, 2, 3, 4, 5, 6, 7, 8, so it's p8 that it's written here. So this is the degree sequence of p8. So, and we know that this graph is graphical, so we can draw this. So we'll see later on an example on how to draw a graph using the degree sequence. So you have also an exercise like this in the practice. So now show that there's precisely one graph that has degree sequence 5, 3, 2, 2, 1, 1. So here they are not asking us to prove that the degree sequence is graphical. They are telling us it's graphical and draw the graph. So we know that we have 1, 2, 3, 4, 5, 6, 7. So I have 7, not 7, 1, 2, 3, 4, 5, 6 vertices. So those are the 6 vertices. So I know that the first one is linked to 5 vertex, so I draw that. Then I have vertex which connected to 3, so I will pick the first one because I will link them, label them by order, and you should do that also in the practice. So B, it has of degree 3, so already it has 1, so I need to link it to 2 other vertices. So okay, I link it to BD, and then I have C, so C, it has already 2, D already 2, E is equal to 1, and F, the degree is equal to 1. So this is the graph. There's nothing else to do, and that's it for the drawing of this graph. So as I have told you, it's very difficult to prove the isomorphism, and there's no efficient algorithm for distinguishing non-isomorphic graph. So however, there are techniques that works well for moderate sized graphs based on what we call a graph invariant. So a graph invariant is a function defined on graph with the property that isomorphic graphs take on the same function value. So we'll see what does it mean. So a graph invariant means the number of vertices, number of edges. So those doesn't change from graph to other if we are considering the isomorphism. So this is why showing that two graphs have different value for a given graph variant prove that two graphs are non-isomorphic. So let's see what kind of graph invariance we have. So we have the number of vertices. So if the number of vertices are different, obviously they are not isomorphic. We have the number of edges. So obviously if the number of edges is different, they are not isomorphic. The number of components. We have also degree sequence. If they are different, so obviously they have different degrees. We have the lengths of the geodesic passes. So if we can find a geodesic different geodesic passes between any two vertices, so obviously this is not isomorphic. So also we can check the length of the longest pass. So here we are trying to find something that doesn't work in order to say that two graphs are non-isomorphic, and also the degree of a neighbor of a unique degree. So degree of neighbors, as we have seen and done in our example. So I'm looking in the neighbors if they have the same degrees. So this is for the graph isomorphism and the degree sequence. So let's see what will happen if I'm considering trees. So we know that for the graphical sequence of trees, so we know that the degrees, if I have a sequence S which is equal to D1, T2, D3, Dn, if I do the summation between the Di, I equal 1 to n, is equal to 2 multiple n minus 1. So why it's equal to multiple n minus 1? Because we have seen that the number of edges is equal to number of degrees minus 1, and we know that each edge contribute 2 times for each degree in the tree, so it's equal to 2n minus 1. So the sum of the degrees would be equal to 2n minus 1. So even if I gave you a degree sequence, you can check this if it's to see whether it's graphical or not. So for non-isomorphic trees, so for trees the most useful of this technique is comparing degree sequence, looking at longest passes and looking at shortest passes between vertices of a given unique degree. So this is why we have an example here. So find a structural property of trees T1 and T2 that show that they are not isomorphic. So we are telling you that these trees are not isomorphic. So and find why it's not isomorphic. So first, we see that both they have 9 vertices and both they have 8 edges, and even if the degree sequence, if I will write it, it is the same. So it's equal to 4, 3, 3, 1, 1, 1, 1, 1, 1. So it will not help us to distinguish this using these properties. So we need to find other stuff. So I will just talk a bit just in order for you to try to find something that doesn't work here. Maybe you are looking about neighbors, maybe you will see. So meanwhile I will write the degrees. So I have here 1, 1, 2, I have here 4, 1, 1, 3, 1, 1. So I have here 1, 1, 1, 1, 1, 3, 4, 3, 1. So we have the same sequence degree, but there's something that it's not correct. So here we have 3. So this is, so as you can see, so we cannot there's something wrong in terms of distances. So if you can look here at 4, this is 4 here. So the distance between the first neighbor, so the shortest pass here between any 2 vertices of degree 3 from 4 is equal to 1. However, if I'm looking here, the distance, the geodesic path, because there's only geodesic passes in trees. So here we have 1 and here we have 2. So this is non-preserved property. So this is why those graphs are not equal, because the distance between the vertices of degree 4 and degree 3, it's not preserved. Also the distance between the degree 3. So for example, here the distance is equal to 2. However, here the distance is equal to 1, and this is not preserved in the graph T2. So this is why our graphs, they are not isomorphic. So they are telling us here in this exercise that there are 6 trees that have 6 vertices, and try to draw them. So you need to have 6 vertices and just 3. So I already have the solution, but I'll try to do it with you. So I have 6 vertex. So obviously I have first the path, because there's no repetition. So I can remove one of these add vertices, and for example place it here. So it's the same if I place it here, and then I have one in the middle. I can also, so I will reduce now the pass here. I will do it with 4. So obviously if I will do that, it will be equal to that, to this one, because they are isomorphic. So obviously I will put them in the middle. So this is also an example. I can also keep it with 4 and place one above one at the end. So the same if I have a mirror, so it will be the same. And so those are with 4, and then I will end up with 3. So obviously if I will put them on the extremities, I will not gain anything. I will try to put 1 here, and I will put 2 here. So those are the 6 trees that have 6 vertices in our case. So we'll end up with the last part, which is about the graph operations. So in graph operations, we will talk about first the union between two graphs. So if I have a graph J and graph U, so if I'm talking about the union, so it means I have the union of the vertices and the union of the edges. So for example, here I have P3, which is equal to P3, and I have P4, and I have then the union. So union, I just put them next to each other. There's nothing more than that. So join is a more bit difficult or more complex to do. So, and we say that the join of disjoint graph of G and H, so denoted G plus H, so it's formed by appending to the graph the union of the two graphs, so the edges, so I will append edges that it's the one vertex is on the first graph and the second vertex is in the second graph. So if the both graphs have m and n vertices, so we must add m multiple n vertices. So we are adding all the vertices, all the edges, sorry, between the two sets of vertices. So this is P3 plus P4. So for example, wheels, so it's we call it W. So for example, 1Wn is equal to K1 plus Cn. So wheels are the join between K and a C, between a K and a C. So we have an example here. So draw the wheel W13, 14, and 15. So this is the cycle, the C3. So W13 is equal to K1 plus C3. And then I have K1 in the middle, and I need to link K1 with all the others. So this is the wheel W13. So for the wheel W14, so this is C4. And then I have K1 here, and I need to link it to all the others. So the same applies for the other example, W15. So as you can see, this graph, I can draw it differently. So I can move this to here, so it will be equal to like this. And if you know well, W13 is equal to K4. So it's isomorphic to K4. So we have also other type of operations. We have edge and vertex deletion. So we call it's graph minus V, where V is the vertex or edge. So if V is a vertex, the graph G minus V is the graph formed from G by removing V and all edges incident with V. So we have here an example. I have the graph here V, and I have removed the vertex V. So if I remove vertex V, obviously all these will disappear, and I will end up with this. If I will remove the edge E, I will just remove the edge E. So the vertices will remain in their place. We have the operation complement. So the complement of graph G is called G bar. So we have the same set of vertices. However, the edges are those that lags from E. So if I have a vertex UV and G, I will not find it in G bar. And if there's one edge is missing in the first one, I will find it in the other one. So the complement of this, and we have some property here that the complement of the join is equal the union of the complements. So obviously, because in the join I'm adding more vertices, more edges, sorry. So obviously in its complement I will end up with the removal of these edges. So, and we say that the graph is self-complementary if the graph is isomorphic to its complement. So we'll see that, and in the practice you will have an example of a graph that is self-complementary. And we have also a property that for any self-complementary graph, the order of n, it means the number of vertices is equal to 4k or 4k plus 1 for any positive k, and the number of edges, so the size, is equal to n multiple n minus 1 over 4. So if we have this, if we have a graph that is self-complement, we know that the order is equal to 4k or 4k plus 1, where k is a non-negative positive integer, it's a positive integer, and the size, the number of edges, is equal to n multiple n minus 1 over 4. So this is why we have directly a question. So they are running a find all self-complementary graphs of order at most 4. So we have the order at most 4. So it could be 1, 2, 3, 4. So is there stuff like that? However, we know that in the course that the order of a graph is equal to 4k or 4k plus 1. So if I will pick k equal to 0, I will have 0 or 1, so obviously there's no 0. And if I pick k equal to 1, it would be 4 and 5. So the options that I have, the order must be either 1, 4 or 5. So they are telling us at most 4, so we are not talking about 5. Now you will do that as a practice. So I will tell you at the end what is the number of self-complementary graphs of order 5. So we know that if I have order number 1, and it means a graph with only one vertex, so it's k1. So k1 obviously is self-complementary, because if I want to draw its complement, it's the same. So we know that the self-complementary graphs of order 1 is only k1. Let's see the graph of order 4. So for graph the number of 4, this is the graph. Let's see, I have this graph. So the number of edges is equal to 3. So we know that if it's self-complementary, so I know that I have 4 multiple 3 over 4. So the number of edges should be equal to 3. So edges equal to 3. So we can, if I want to draw all the possibilities, we know that there are 3 graphs with 4 vertices and 3 edges. So let's do that quickly. So I have k3 union k1. I have k3 union k1. So this is the first one. I have p4. This is 4 vertices and 3 edges. And I have the k1, 3. So it's k1. And I have 3. I have 4 vertices and 3 edges. So which one is self-complementary? So I will try to draw that to see which one is self-complementary. So I will draw this. So I have 1, 2, 3, and 4. So in the self-complementary, it means that I will draw the missing edges. So I have here all they are linked. Only this is not linked to all others. So I will have this. So obviously this one is not isomorphic to those one, because here I have degree 1, 1, and 3. Here I have 2, 2, 2, and 0. So obviously they are not equal. I will do this one. So I have this. So this one is linked to all 3. So all the edges will disappear. I will have 1, 2, and 3. So obviously those they are not isomorphic. Let's draw the complementary graph of this graph. So I have 1, 2, 3, 4. I need to link, so I have this linked to only this, so I need to link them to the other ones, right? And this one is linked to those, I need to link it to only this one, and the same this, I will link it to the first, so the third one is already linked, and this one I will link it to the first two. So as you can see, if I want to redraw it differently, it will be equal like this. And yes, this one is isomorphic to this graph. So we have found that only one graph is self-complementary. So for order equal to 4, I have just P4 is self-complementary. So we know, so for order 5, so the number of edges is equal to 5. So there are 6 graphs with 5 vertices and 5 edges. So we know that only C5 is self-complementary. So we can, I don't know what's this. So we can just try to do it by your own to prove that C5 is only the self-complementary one. We have also other operations like the Cartesian product. So we have 2 graphs, G and H. So each one has a set of vertices. So let's say the first one has m vertex and the second has n vertex. So we say that the Cartesian product, so G cross H, so is the graph with the set consisting of vertices labeled from the first one and the second one. So let's say that we have here the set of vertices u1 um, and let's for H we have v1 vn. So I will take all the combinations ij, so this is the vertex, such that I is between 1 and m and j is in between 1 and n. So we take all the combinations, so we'll see that we have a very big number of vertices. So, and how we will link these vertices? So we will say that, let me erase, so I have ij vertices. So let's say that I have ij, I will link it, I need to place an edge with hk. So how can I do that? So those are two vertices in my Cartesian product. So if I is equal to h, and if the vertex j is adjacent to vertex k in G, so this is in H because the first one are equal. So if the first one are equal, I will see if there's an edge in the second graph, and if the second parameters here are equal, and I need to check if there's an edge between ui is an adjacent to uh in the first graph. So it's very tricky. So this is why we will see how it will be constructed. This is a very important operation. So we call an edge of the first type an edge, obviously, and an edge of the second type gh, because as you have seen, as we will see later, that since the contribution comes from the second graph, it's called edge, and if it comes from the first graph, it's called g edge. So for each I, it means for each vertex, the induced subgraph on the vertices I and j. So whenever we say it, so if the vertex comes from I, we call it I's H copy, and if it comes from j, we call the j's g copy. So we'll just be focused on the drawing of the Cartesian product. So we have here two graphs. G is k1 plus k2, so I'm doing the plus. So this is k1 and then k2 k1, so I will link them with edge, and then I have k2, so I will link both k1 plus k1 with k2, and then I have p3. Now I need to draw the Cartesian product. So I have here a lot of possibilities, since I'm doing the cross product, Cartesian product between g and h. So I have 1 1 1 2, I have 1 1 here, 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3 and 4 1 4 2 4 3. So I have all these vertices. Next, so 1 1, so I will see, so 1 from the first graph and 1 from the second graph. So I will have also 1 2, so I will draw 1 2, I don't draw it. So yes, is there a link between 1 1 and 1 2? So let's see. I have 1 from the first graph and 1 from the second graph, and I want to see if it's linked to the other graph. So I can see that this is 1 2 from this graph, so 1 from 1 2. So I can see that 1 is equal to 1, so this is here. So I need to check if 1 2 are linked in the second graph. So I can see yes, it's linked in the second graph, so I will place an edge here. So the same here, I have 1 2 1 2, so 1 1, it means I will look in the first graph for the vertex equal to u1, and then I will see if there's an edge between v2 and v3. Yes, there's an edge between v2 and v3. So and we'll go like this. So we'll see it will be constructed like this, and at the end we'll have the Cartesian product between these two graphs. So it's very easy to construct whenever you understood how we do that. So the vertices here in the Cartesian product is a pair. So the first one we look the first graph, and the second we look at the second graph. So let me give you, for example, this edge. So I have here 1 1 2 1 1. So 1 1 I will look at the so this is vertex v1, and I will see if there's an edge between 1 and 2 in the first graph. So yes, there's 1 and 2 in the first graph. So let's see why, for example, there's no edge between 1 and 4, for example, here. So there's no edge 1 and 4. I have a vertex for 1, so it's linked to 3 1 3 2 and 3 3 because it's obvious here, and it's linked to 4 1 4 2 and so on because of this part, and this part is for linked to 3, but it's not linked from 1 to 4 because there's no link between 1 and 4. So the cross product is very important in what we call hypercubes. So an important class of graphs that can be defined on terms of the Cartesian product operations, which are the hypercubed cubes. So they are very important, especially in parallel computing. So a hypercube is defined recursively, so I will give you that. So the stopping condition, so Q1 is equal to K2 and Qn is equal to K2 multiple cross product of Qn minus 1. So in other words, K is 2 copies, so Kn is taking 2 copies of Qn minus 1. So recursively, we are doing that. So the name hypercube comes from the fact that Q3 is drawn as a cube on a 3 dimension, and the concept can be extended to a higher orders. So we say that the Q1, for example, we label it usually using a binary notation, so 0 and 1. So Q1, so it contains just 2 vertices. So Q2 is 2 copies because Q1 is equal, as we have seen, is equal to K2. And Q2 is 2 copies of K1. So we will label it 0, 0, 0, 1, 1, 0, and 1, 1. So obviously, we append just 1, 0, and 1, 1, and so on with the Q3 and Q4. So usually it differs by 1 bit. So we have here the drawing of the first 3 hypercube. So as we see, the third hypercube, it's composed of labeled inner and outer copies of Q2. So we have this one Q2 and this one Q2. However, so this is the outer, we have just zeros, and here we have appended 1 to those values. So this is how the constructions of hypercubes occurs. So we know that a vertex set of Qn, it's all the binary strings of length n. So it means that we have just digits of 0 and 1. So we have 2 power n possibilities. So we know that the vertex set of Qn, the number of vertex set, is equal to 2 power n. So since the recursive definition of the hypercube, we see that the degree of each vertex, if you can see here, is equal to 3. So it's equal to n. So Qn is n regular. So also the hypercubes are n regular. And usually each number, so any adjacent vertex, they differ by just 1 bit. So this is for hypercubes. So we end up with meshes. So a mesh also can be formed using a Cartesian product. So we have a mesh, or we call it grid, or we call it a lattice. So the two, a mesh m and n, it's the Cartesian product of Pm multiple Pn. And also the 3 mesh is equal to PA multiple PB multiple PC, and we can generalize to n meshes where we have the Cartesian product of passes. So let's see an example. So this is an example of 2 mesh M43. So it's P4 multiple P3, and here we have the 3 meshes, P3 multiple P2 multiple P3. So we have here just labeled some of the vertices. So you can see the 3 meshes M323 is like a parking garage. So we have several identical levels, C to be exact, because they have C levels. So this is C, 3 levels. The third coordinate identifies the level. So each level is a 2 mesh. It's B. So there's so each level is a 2 mesh with B rows and A columns. So if A, B, and C are very large, so it's very useful to memorize the location of your car. So you can place it here, 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 or here. So it depends on this. So usually meshes represents these sort of graphs, usually parking garages. So there's also two operations, the line graph and the contraction. So whenever I have a graph, so the line graph has a vertex set consisting of the edges of G. So it's a bit the opposite. So I have here AB, the edges AB, AC, BC, and CD. So I will consider AB as an edge, AC as an edge, BC as an edge, and CD, and then link all these together. So 2 vertices in the line graph are adjacent if the corresponding edges of G has a vertex in common. So for example, we have these examples. So we'll see later the usage of line graphs. We have also the edge contraction. So whenever I have a graph, I can contract edges. So I will replace an edge with a vertex. So for example, here I have, so the notation is like this. So it's bar, U and V, to say that I'm contracting the edges U and V. So we remove both vertices U and V, as well as any edge incident with them, and then inserting a new vertex, and we call it with a star. So let's see here the VW. So I have removed VW, I have used VW star. So obviously X now will be linked to VW star, T to VW star, and U to VW star. For example, here I'm doing the contraction of the edge TX. So in TX, obviously U will be linked to TX, W and TX, and this is it. So this is it for this chapter. I know it's a bit long and there's a lot of things to understand and to learn, but you will have the practice that you need to finish in order to access the second chapter. And if you have any questions, do not hesitate to write to me, and see you in the next chapter.